Hi everybody. Um, I am going to be going through this O-level multiple choice paper for physics in preparation for your exam. I encourage you to first try this exam by yourself and then come back and take a look at the way that I show how I solve it. So if you're watching this and you haven't yet gone through the exam, stop the video and try it out for yourself first. Okay, without further ado, let's get started. Now, the first question says, which word is the name of a vector quantity? Now you'll remember that a vector has to have direction and magnitude. Density doesn't have a direction. Displacement does have a direction. Displacement is essentially a vector which points from a starting point to an ending point. So basically, if I move an object from one point to another, that would be its displacement vector. So indeed, the answer is B, displacement. I once heard that most multiple choice answers are B. Probably not a great strategy to use to answer your science questions, but there we go. Let's just, for the sake of completion, take a look at the last two. Energy. Can energy have a direction? No. And speed is a scalar. The vector form of speed would be called velocity. So in conclusion, the correct answer is B, displacement. Great. Next question. What is the size of the resultant of the two forces shown in the diagram? So we've got a force that's heading upwards, and we've got a force that's heading to the right. 3 newtons plus 4 newtons. And so the way that we add them up is what's called the tail to head method. So here would be one vector, and now I'm going to add another vector. However, this vector's tail will be appended to the head of the previous vector, like that. And then we're going to have a resultant vector, which I'll color in another color. Let's try blue. And so the resultant vector will be a vector pointing from where we started to where we ended up. There's our resultant. Now, you can go and draw this and actually measure it. Or you can use Pythagoras. And what we've got here is the famous 3, 4, 5 triangle. And so the correct answer is 5 newtons, up and to the right. Next question, let's see here. What's the correct unit for the quantity shown? So I'm just going to go through them. Electromotive force, unit newtons. Latent heat, unit joules. Pressure, kilogram per meter cubed. And weight, kilogram. The correct answer is B. Now, why is it B? The answer is B because, okay, let me go through them one by one. Electromotive force is measured in volts. It's an electrical driving force. Latent heat, now a scientific word for heat is in fact energy. And energy is measured in joules. Latent heat is the amount of energy required to heat up an object. pressure is not measured in kilograms per meter cubed. It's measured in newtons per meter squared. Newton being a unit of force per area. Finally, we get to weight. Now, a lot of you might have thought that this is right, that weight is measured in kilograms, like I weigh 50 kilograms. However, I'd like to remind you that weight is a force, and therefore it's measured in newtons. Mass is an intrinsic property of matter measured in kilograms. This is technical physics talk, of course. Okay, let's try this next one out, number 4. A length of copper pipe of uniform cross-section and several meters long carries water to a tap. Measurements are taken to determine accurately the volume of copper in the pipe. Which instruments are used? Well, a micrometer and a rule, micrometer and calipers, a rule and tape, or finally tape and calipers. In order to measure the thickness of the pipe, one can use calipers. You could also possibly use a micrometer, but a micrometer is more used for extremely thin or small objects, like a human hair or a piece of paper. And you measure in microns. I don't think we're going to be measuring the thickness of this pipe quite in microns, maybe in millimeters. Therefore, I'm going to opt for the calipers. And another thing we're going to need to measure the volume of copper is the length of the pipe, which I think we'll measure with tape. So in conclusion, I will say that tape and calipers will do the job for us. Okay, next up we have a speed-time graph, 2 runners. It's important to note that it's a speed-time graph. So, maybe runner 2 is running at 10 kilometers an hour, and runner 1 is running at 20 kilometers an hour, or something like that. Think about it that way. Okay, which statement must be correct? Both runners started at the same moment. Must that be correct? I don't think necessarily. Remember they said it's only part of a speed-time graph. Maybe we didn't even see the beginning. And there's nothing here which shows that where they started. So I'm not convinced that A is the correct answer. Runner 1 has a greater acceleration than runner 2. That's also not correct, because acceleration is when you increase speed, or decrease speed, or change your speed. Now they're not changing their speed, so they're not accelerating. They're running at a constant speed, as you can tell, because of their speed being flat. So not right. Number C, runner 1 is moving faster than runner 2. I don't think that's controversial. That's obviously correct. The distance between the 2 runners stays the same. Now, the distance on this graph does stay the same, but that doesn't mean the distance between the 2 runners stays the same. If you have a runner running at 10 k's an hour and another runner running at 20 k's an hour, the distance between them will grow. If it was a displacement time graph, that would be true, but it's a speed time graph. Cool. Next up, another speed time graph. This graph shows how the speed of time of a car varies with time. Now they're asking us about the acceleration of the car between the times 10 and 20 seconds. What do we say about that? The speed remained flat. The speed didn't change. So is it correct to say the acceleration decreases? The acceleration increases. The acceleration is constant but not zero, or the acceleration is zero. If your speed doesn't change, then you're not accelerating. And so Gonna make me ovals. So the acceleration is 0. Yes. In which descent is the acceleration equal to the acceleration of free fall g at all times? At all times. Let's think about each one. A bungee jumper leaping from a bridge. Well, initially they do accelerate at free fall. Later they slow down, mercifully, before they hit the ground. So I don't think that's true. A feather falling in a vertical tube that contains a vacuum. That will fall at the free fall speed of g. At all times? Yeah, until it hits the ground. So maybe B, eh? Remember that in a vacuum, there's no force that's retarding you, that's holding you back or slowing you down. Unlike in air. A hailstone traveling to Earth at terminal velocity. Now, if you're at terminal velocity, you're no longer accelerating. So therefore, we can't say that your acceleration equals to g, which is 10 meters a second squared. You're no longer accelerating. Finally, a skydiver also reaches terminal velocity. So he also stops accelerating. Hence, the correct answer is, in fact, this one. Feather falling in a vertical tube. Next question. A body slides down a frictionless slope, as shown. As the body presses on the surface pushes back on the body. In which direction does the surface push back on the body? What do you think is the answer? Is it A, B, C, or D? So we're asking, in which direction does the floor push back? And then, in fact, the correct answer is the floor always pushes back at a direction normal to its surface. And that is C. Okay? Not B. There are in fact two forces acting on this body. There's weight, which acts downwards, and the normal force, which always acts normal to its plane, meaning at right angles. Okay. The Earth travels at a constant speed in a circular orbit around the Sun. Which arrow shows the direction of the acceleration of the Earth? And the direction of the velocity of the Earth? Okay. Bit of a tough question, this one. Currently, the velocity vector of the Earth is given by Q. It's heading in that direction. And that's its velocity. Now, if it weren't for the fact that it was accelerating towards the Sun, it would continue on this straight path. There's something that's pulling it inward into a circular path. That's a force. That force is gravity. Gravity acts towards the Sun. And you might remember that force and acceleration are related. F equals ma. That causes an acceleration towards the Sun. Okay? Hence, this is the velocity, and this is the acceleration. Q is the velocity, and R is the acceleration. That gives me answer D. Okay, a student balances this object, which is not a uniform object, on a pivot. To do this, the weight is suspended near the left-hand end of the object is shown. Okay. Where is the center of the mass of the object? Well, it said that the student balanced it. Now, if you want to balance something, you have to put the pivot under the center of mass. So it has to be C. If it's balanced, it's C. Even though that might not be the natural center of mass of the object. This actually makes me realize it's a trick question. The object plus this weight have a center of mass here. Now, what do you think about just the object itself? This is actually not the right answer. Okay, think about what would this weight do to the center of mass? Would it move it to the left or to the right? I think we would move it to the left because it's an object that's on the left. Hence, the correct center of mass is actually at D because, well, as you can tell, this object is more skewed to the right. It's got more stuff on the right, so its center of mass will be more to the right. I'm going to go with D. Great. Next, another physics question they love to ask. Let's see here. The difference between two springs in parallel and two springs in vertical. Really, if you try this yourself with elastic bands, what you're going to find is when you take two elastic bands next to each other like this, it's going to become twice as stiff, twice as difficult to extend. Try it for yourself. And then if you take two springs or two elastics and tie them together one after the other, compared to the original one, it's actually twice as easy to stretch. That's because it's longer. Basically, longer stretchy objects are easier to stretch than shorter stretchy objects. So in comparison to a single spring, this one is twice as easy and this one is twice as hard. So in comparison to each other, this one is now 4 times as easy to extend. So it's 4x. Yeah. Next question. This diagram shows 3 tubes, P, Q, and R. Each tube contains air, trapped by a water column. Okay. Which statement is correct? The pressure in the trapped air is equal in tubes P, Q, and R. The pressure is the greatest in tube Q, or R, or P. Now there is a formula for pressure. Pressure equals rho times G times H. And H is vertical height. And there'll be one thing you'll notice about all 3 of these. They all have the same vertical height. Even though they've got different arrangements. Q is thicker and R is more skewer. They've still got the same vertical height. And that's all that matters. Hence, the pressure will be the same, because they've all got the same vertical height. Obviously, all got the same density and same gravity to them, so it will be equal pressure. Which graph shows the relationship between the pressure and volume of a fixed mass of gas at constant temperature? So, the thing about it is, as you make the volume greater, what's going to happen to the pressure inside of a chamber? So, let's imagine a piston with some gas in it, and now I expand the piston, thereby making the volume bigger. what do you think will happen to the pressure inside? One way to do this is to take a little syringe and sort of pull it out like this. The pressure will go down as the volume increases. And so the correct answer is C. And now B also has the pressure going down as the volume increases, but in a linear manner. When things are inversely proportional, you get a shape of a graph like this, not a linear graph. The correct answer is C. Okay. An object X has mass m and velocity v. A second object has mass 2m and velocity 2v. And so, how much greater is its kinetic energy? Now, as you know, kinetic energy equals to half mv squared. I'll just leave it like that. It's mv squared. Okay. So doubling the mass will double the kinetic energy. But doubling the velocity will then multiply the kinetic energy by 4 because of the square relationship on the velocity. So essentially it's times by 2 and times by 4. And so in conclusion it's times by 8. There is another way you can do this by subbing in 2m in here and 2v in there and comparing it to the original. And because 2v squared in brackets is 4v squared, that means 4 times bigger. And then there's the other 2 as well. 4 and 2 together getting you 8. So this object's twice as heavy and twice as fast, now got 8 times more energy. Where is energy released by the fusion of hydrogen nuclei to form helium? A, in a nuclear power station. No, we don't yet have fusion nuclear power stations. Our nuclear power stations work on fission. In a radioactive isotope emitting alpha particles. Again, that happens through radioactive decay, usually of quite a heavy or large nucleus, not of a hydrogen nucleus. In fact, think about it. How can a hydrogen nucleus form an alpha particle? In the core of the Earth? No. I don't think there's hydrogen in the core of the Earth. And in the core of the Sun? Yes. This is what fuels the Sun, is hydrogen fusing into helium, which is tremendously energetic. Cool. A student uses a Newton meter to pull an object distance d horizontally along a flat surface in a time of t. The Newton meter reading is F, so a certain force F. What is given by the expression force times distance divided by time? Is it efficiency? Is it energy? Is it power or work? Work, this is not working. Work is equal to force times distance. Work is also equivalent to energy. Work per unit time, or energy expended per unit time, is power. That is the rate at which you do work. So the correct answer is power. Cool. For some reason, didn't want to make it into a nice oval for me there. Oh well. Okay, students given a thermometer that reads 1 degrees Celsius in pure melting ice and 101 degrees Celsius in pure boiling water. She uses it to measure the temperature of the water before and after it's heated. How does the rise in temperature of the water calculated from the result compare with the correct value? Okay, this is interesting because when we calibrate a thermometer, we set it to 0 on melting point of ice, and we set it to 100 at the boiling point of water. Whereas her thermometer clearly has an error. Everything is shifted to the right by 1. However, the scale is still 100 degrees. So in a way, her thermometer, you can just correct it by subtracting 1, right? Everything is just off by 1. It's 1 too much. Now the question is, will that make a difference in terms of comparing the difference of temperatures you measure? It won't actually make a difference. Let's say that she's heating up water from 30 to 60. Okay, that's a change of 30. But her thermometer is going to heat it up, it's going to measure it from 31 to 61. But because 61 minus 31 is still 30, she will still get the correct value for the difference, even though she didn't get the correct value for the actual measurements. The difference is still correct. So let's be the same. We are the same. A student makes 4 statements about evaporation and boiling. Both involve an increase in molecular separation. Well, I'd say evaporation a lot more than boiling. In fact, the difference between liquid and solid in terms of their separation isn't very much. In both instances, the molecules are pretty much next to each other, but in a gas they're far apart. Okay, so I don't think 1 is correct. Number 2, both occur at a fixed temperature. Oh wait, sorry, evaporation and boiling, not melting and boiling. Let me think about that. Both involve an increase in molecular separation. Sorry, that is correct. It's almost the same thing, evaporation and boiling. It's turning from a liquid into a gas, and that means your separation will increase a lot. So I'm sorry, 1 is correct. Both occurred at a fixed temperature. No. Evaporation can occur at any temperature. Only boiling happens at a fixed temperature. Both involve the absorption of thermal energy. Yeah, they do both involve the absorption of thermal energy. Like when you get out of a pool and you feel cold because of evaporative cooling, that's because it absorbed energy from you. And also, when you boil water, it absorbs energy from something, like a stovepipe. Both occur through the liquid? No, only boiling occurs through the liquid. Evaporation takes place at the surface. So that leaves us with 1 and 3 to be correct. So we're going to go with 1 and 3. Bam. Look forward to seeing how I did on this exam. How is specific latent heat defined? Let's read through them. The heat absorbed or emitted by a unit of mass during a change of a state without a temperature change. The heat absorbed or emitted by a unit mass during temperature change. The heat absorbed or emitted during a change of state without a temperature change, but not per unit mass. The heat absorbed or emitted during a unit temperature change. I think it's B. It's basically how much heat does it take to heat something up per unit mass. Now, when you've got a change of state, like melting or boiling, during that period, actually the temperature doesn't change. It actually stays constant, right? So that's what they say without a temperature change. We give that another name. We call that heat of fusion, or what is the other one? Anyway, that's the energy required to melt something. It's not the same as latent heat, which is how much energy it takes to heat up something by 1 degree. Yeah, it's measured in degrees per joule kilogram. Yeah, so it's 19 is number B. Bit of a technical question there. I'm happy to answer everybody's questions regarding these, so please send them in if you have any questions. If everything isn't clear, just ask me. Okay, let's check out this next one. A syringe containing air is sealed at one end. The piston is free to move. Now the air gets heated. Now what do you think is going to happen? If this piston wasn't free to move, now these air particles are going to get more excited, but nowhere to go. So all they can do is just bang on the sides of this wall, and that's going to increase the pressure. But since the piston is free to move, this increased pressure will then cause the piston to go out, and this gas will expand. So the gas will expand when we heat up this gas. Heat up that air. Now, because the gas expands, the average distance between the air molecule will increase, and the density will decrease. So I'm going with A. Looks like my theory of most things being B is not so much working out. So not a great strategy to go with if you didn't study at all. Looks like we're about halfway. Hopefully we're about halfway. Let's see how much a little bit of 40. Just over halfway. Okay, a metal disc gets heated up to 600 degrees and then it gets lowered into a beaker of water. What happens to the mass of the metal disc? The mass of the water? Well, it might depend on what happens to the objects, but I don't think the mass of the metal disc is going to change at all unless it reacts with the water. So assuming it doesn't react with the water, I'm going to go with no change. But surely that's going to cause some steam, right? So this thing's pretty hot. Putting it in some water, you can imagine some steam will be released. And because some steam will be released, the mass of the water in the beaker should decrease. So I'm going to go with C. What description defines the amplitude of a water wave in a ripple tank? Amplitude is how high a wave is, and you measure it from the middle to the peak. You don't measure it from the trough to a peak. You measure it from the center point. So in other words, it's half of the vertical distance between a trough and a peak. Okay? That's the right answer. Half the vertical distance between a trough and a peak. That is amplitude. Next we have a question about wavefronts. Wavefronts are circular. It's circular emanations coming from a disturbance. If you imagine throwing a pebble into water, it will cause circular emanations. Okay, let's see what they have here. Wavefronts from a point are straight lines. No, they're circular. Wavefronts from a point source are circular. Wavefronts are parallel in direction of energy movements. Yeah, I think that's correct. Wavefronts are perpendicular to the direction of energy movement. I don't think that's correct. I think it's 2 and 3. I'm going to go with 2 and 3. Okay. And objects placed in front of a mirror, plane mirror, and okay, there's the object, and there's the image. A ray from the top of the object is mirror. It's incident in the mirror at X. I'm actually going to draw that for us, okay? So we've got a ray coming from here, from the top of the object, going down to X. Cool. Now what's going to happen to this ray? Well, it's a mirror, so it's going to reflect. So, it should do this. Like that. Remember, this is a virtual image. Light doesn't actually go here. There's nothing back here. Light doesn't go through this thing. Your brain imagines that there's something there. There's actually nothing there. So, okay, let's see here. It reflects as if it came from the top of I. Yeah, that's correct. It reflects, and you think that it's coming from the top of I, because it came from the top of O. And so your brain thinks that it came from there, tracing this ray backwards logically would make it think that it came from there, which is why you get the virtual image there. Okay, that should be a dashed line, but that's the correct answer. So hence the correct answer is D. Yes. Okay. This diagram shows light passing from glass to air. What is the name of angle P? I might struggle with this one. Angle of incidence or angle of reflection, angle of refraction. Or is it the critical angle? It's not the critical angle, otherwise this ray would be going along there. So that's one straight out. It's also not the angle of reflection, because I don't see reflection happening. More like, is it refraction or incidence? I'm not actually sure. I'm going to go with angle of incidence. I might be wrong about this one. I guess we'll check. This is the first question that I've really been a little bit uncertain about. So I'll just have to validate myself over there when we come back to this. Objects placed in front of a converging lens are of focal length 4 centimeters. The height of the image is 6 centimeters. Okay. What's the magnification formed? Now, this is actually real easy. The image is bigger than the actual object. Object is... Oh wait, no. Let me just read out the screen. Focal length is 4 centimeters. So there's our focal length there. That's 4 centimeters. And that's also 4 centimeters. So in other words, 1 square is 4 centimeters. And one of the easiest ways to do this is just measure the height of this object and compare it to the height of that object. So looking at this object, it's 1.5 big squares in size, okay? Whereas this one is 3 big squares in size. So that means it's got magnified by 2x, because going from 1.5 to 3 is a multiplication by 2. It's just how much bigger is that than that? It's twice as big. Okay. Speed of sound in air, liquid, and solid. Okay. Speed of sound is the fastest in a solid, second fastest in a liquid, and it's the slowest in the gas. So I'm going to say solid, liquid, gas. Going from slowest to fastest, it'll go air, liquid, solid. Air, liquid, solid. That's number C. Cool. A man stands 80 meters in front of a cliff face. He makes a loud bang and listens for the echo. He makes a loud bang once every second. He hears an echo exactly halfway between those. In other words, it takes half a second. It takes half a second for it to travel 80 meters and then another 80 meters back. So we can do 160 meters in half a second. So if you can do 160 meters in half a second, then in a whole second you can do 320 meters. So it's 320 meters a second. If you want to, you can go to your calculator, you can do 160 over 0.5 and get 320. But 320 is the correct answer, and that is kind of close to the speed of sound in there anyway. So yeah. Really not having a lot of B's here. Cool. This diagram shows two magnetic field lines of the magnetic field around two bar magnets. Okay. Which row shows the magnetic poles at P and Q? Now remember, these things go from north to south. The arrow points in the direction a compass would point, and a compass points north. Okay. And north gets attracted to south. And also these lines go from north to south. Hence P is a north. This is a north and that's a south. Okay. And we see that there is also something leaving here. Now, again, it leaves away from a north going towards a south. So that's a north, meaning that that's a south. So P is a north and Q is a south. P is a north and Q is a south. Oh, there's a B. If I said that all a bit quickly and it was a bit confusing, try figure it out for yourself and then come back to this video. Don't just listen to me the first time and like listen to me figuring it out. You have to figure it out for yourself. Use this video to check that you did it the right way. Metal plates attached to Earth by a battery. Yeah, this symbol means Earth. The plate has a positive charge. A second plate is initially uncharged and connected to the Earth. One of these questions. What happens if you bring Y close to X? Wow. It's positive charges here. It's going to attract negative charges here. So because negative charges get attracted here, the electrons actually flow up from the Earth towards Y. So that's B. B. Remember, protons don't flow. Okay, protons don't flow. Not in solids, they don't. They stay put. Electrons flow. Okay. Here we got a little house with a metal lightning conductor. Why is a lightning conductor made of copper? It's got low resistance. I mean, yeah, we're going to spend too long on that question. That's the right answer, okay? It's got low resistance. Yeah, both positive and negative charges can flow through copper. Firstly, that's not true actually. Remember, only electrons flow. They're negative. Copper can be electrostatically charged. Okay, no. That's not the point. The point of it is to conduct lightning away from your house. So that's why. So heat is conducted away. No, so that energy is conducted, electrical energy. Which symbol does not represent a power source? This is an individual cell. That's a power source. This is a voltmeter. It's not a power source. This is a AC power source. That little line means it's AC. It's a little wavy shape. And this is just multiple cells, which you call a battery. It's also a power source. This one's not a power source. We're on 33 out of 40. All right. All right, getting there. Resistors of different resistances are connected to a power supply. In either a parallel circuit or a series circuit, which statement's correct? The current is the same for all resistors connected in parallel. The current is the same for all resistors connected in series. The voltage across each resistor is different for all resistors connected in parallel. The voltage across each resistor is the same for all resistors connected in series. Okay. The correct answer is B. Within a parallel circuit, the current doesn't have to be the same everywhere. In a series circuit, the current is the same everywhere. That's the right answer. In a parallel circuit, the voltage is actually the same. So C is wrong. It says the voltage is different. That's wrong. And D is also not necessarily correct. It's only correct if the resistors are equal. So it's B. It's B, guys. Okay, here we come to a bit of an advanced question, looks like. Let's see here. Which one gives the greatest ammeter reading? So you'll have the greatest ammeter reading when you have the lowest resistance. Now, in fact, the more things you add in parallel, the lower the resistance gets. Here we've got 3 of them added in parallel. You've got 2 of them in parallel and 1 in series. Here's another arrangement of 2 of them in parallel and 1 in series, and here they're all 3 in series. It's A which will have the lowest resistance. And lowest resistance means the highest current. A. A hot plate in an electric cooker contains 2 identical resistors. A switch has 3 positions. Position 1 puts the 2 resistors in series. Number 2 puts the 2 in parallel. Now remember, they're identical. And the final one is just 1 resistor. Okay, let's say that they have a resistance of R. 2 of them in parallel would in fact have half the resistance. And 2 of them in series will be 2R. Now, when you've got a higher resistance, it's got less power. The reason for that is because the current goes down, and now you've got less electricity going through, you've got less power. So, the 2 in the series are going to have the most resistance, and that's going to be the lowest power. And number 2, position 2 will be the highest power. So position resistors in series is the lowest power. The correct answer is B. That one took me a moment to figure out, but I kind of checked. No, it's correct. Getting there. A mains electric circuit's fitted with a circuit breaker. rather than a fuse. What's going to happen with the circuit breaker when you put a current that's too large? Now current comes through the live wire, by the way, so we're just going to exclude those ones. That said, I'm sorry. I'm going to go with B over here. Not sure if they're connected to the live or neutral. I might be wrong on that one. We'll have to check. Transformers are used to transmit electrical energy between power stations. So you got your power station and you got a transformer. This is for power transmission. The point, you use a really high voltage. So the transformer is going to kick it up to a really high voltage. That reduces your losses. High voltage implies a lower current. And that's why you lose less. It's B. High voltage means a high potential difference with a low current. Thermistor warms up as the current increases. I believe a thermistor its resistance increases as the resistance will increase as it heats up, right? Now, because the resistance increases, does the resistance decrease? If the resistance were to decrease, the voltage would decrease. Oh yeah. So like A. Check it out. This is like an ohmic graph here where it's got a straight line. And we see that the resistance increases or decreases, meaning that it's got more current than voltage. It's basically A. A because it's a modification of this will be a standard resistor, D. It's a modification of that, okay? It's A. By the way, these guys, they don't make any sense. B and C don't make any sense. Really, the only ones which make any sense are A and D. Okay. Almost done here. We've got 2 more questions. Radioactive substances are used as tracers in medical examinations. A liquid tracer is injected into a patient. A detector 20 centimeters above the patient shows where the radioactive substance is in the body. What should we use? Should we use an alpha particle emitter with a half-life of a few hours, or an alpha particle emitter with a half-life of a few years? A gamma ray emitter with a half-life of a few hours, or a gamma ray emitter with a half-life of a few years? Remember that alpha particles, they can't even penetrate through skin, and this is now in your body. So if it were alpha particles, it wouldn't be able to be detected. Alpha particles can't even go through 20 centimeters of air either. They're really weak penetrating ability. Therefore, it's got to be gamma rays. So the selection is it gamma rays with a half-life of a few hours or gamma rays with a half-life of a few years? Well, which one would you prefer inside your body? I'd rather have it running out in a few hours than in a few years, personally. I'm going to go with C. Last question. We get an isotope of lead, which is lead-212, and it's radioactive. After 3 decays, 2 beta particles and an alpha particle have been emitted. Another radioactive isotope of lead is formed. What is the mass number of the new isotope? Well, emitting the beta particles, which are electrons, is not going to change the mass number. Because electrons, they just almost don't even count to the mass number at all. Electrons weigh almost nothing. So the beta particles, it doesn't affect the mass number. An alpha particle has got a mass of 4. So since we lost an alpha particle, our mass number should go down by 4. So from 212 to 208. Now I'm going to be checking my answers. Okay, here we go with the answers. Sweet. One B correct, 2C correct, 3B correct, 4D correct, 5C correct, 6D correct, 7B correct, 8C correct, 9D correct, 10D correct, 11D correct, 12A correct, 13C correct, 14D correct, 15B correct, 16C correct, 17B correct, 18C correct, 19 is A. Shit. Okay. So I guess specific latent heat. You know what's the it's the giveaway here is latent. I don't know if you guys know what latent means. Latent means that something doesn't change. So it was A, meaning it was in fact during a change of state. And these things are always per unit mass. So really, you might be wondering, it could have been A or C, but A was the one that was per unit mass. It had to be A. So I got that one wrong. It's a bit of a blemish on my record. Not going to lie. I have to study that a little bit. Moving on, I'm a bit depressed about that, but let's see. 20A correct, 21C correct, 22A correct, 23 is D. Messed this one up as well. Turns out wavefronts are perpendicular to the direction of energy movement. Oh, I done messed up. I was picturing these wavefronts expanding little circles, right? And they push a wave forward. So it seems like they're moving in the same direction as the wave, except of course they're expanding in all directions. So yeah, I didn't think about this one properly. Okay, you need to imagine what kind of waves these are. And these are in fact longitudinal waves. It's like ocean waves, okay? And those have got energy going up and down. So even though the wave's moving in one direction, the motion, the energy goes up and down. Like if you're trapped on the ocean, waves coming past you, you move up and down. You don't move left and right. That'll be yet another blemish on my record. So now I'm down 2. So far I got 38 out of 40. Okay, 24D, got that one right. 25A was right. Okay, this one I wasn't so sure about. That said, it makes sense that it's the angle of incidence. Yes, the one coming in and then the one getting refracted. Okay, that's good. Good that I got that one right. 26C. 27C. Nice. So far, so good. 28D. 29B. 30B. 31C. 32B. 33B. 34A. 35B. 36B. 37B. 38A. 39C. 40B. Bam. Total of 38 out of 40 for Mr. Eccles. How did you guys do? Yeah, let me know. That concludes today's little exam prep. Hope you found it useful. We'll be doing a few more of these. Okay, that's it. See you around.